All right. So let's start the second hour. So we were in the middle of this claim, in the proof of the claim. We define EX as the equivalence class containing X, the equivalence class being that 2 points are called equivalent if there's a connected set containing both of them. And here we claim that EX, the equivalence class of X, actually is the union of all connected subsets of X containing X. In particular, EX is the largest connected subset containing X. So that was our aim. Here we showed that any connected subset of X containing X lies inside EX. So this means that EX contains all the connected subsets of X. So EX is this, basically. It is the union of all A's so that X is in A and A as a subset of X is connected, okay? Did we prove this? Not really. Okay, we have this. We have this. So we have this union. Okay, X is in X and A is a subset of X and connected. We showed that this union lies inside EX. Okay. In other words, any connected subset of X which contains X lies inside EX, therefore their union lies inside EX. But remember this, each A is connected and they have a common point, right? Therefore, their intersection, the intersection of these A's is not empty. They all contain the point X. Therefore, their union is also connected. Since the subsets in the union have a common point, namely X, their union is also connected. But so this is the largest, hence is the largest connected set containing EX. But still, I think we haven't proved. Okay, we showed that EX okay, we haven't shown that EX is still connected, right? But that's also clear. Finally, if y is in Ex, then there is a connected set containing, let's say, A containing uh, both X and Y. Hence, this A is one of the A's in this union. Hence, A is one of the subsets in the union. This union. So uh, in particular, Y was in this A, therefore it lies inside this union. Okay. But this means what? Y is an arbitrary point in Ex, right? It's an arbitrary point. Therefore, Ex lies inside this union. But this was already in Ex, right? This union was already in Ex. Therefore, thus Ex is just this. Okay. It is the union of all connected subsets containing X. Okay. So we proved what? We proved that Ex is the union of all connected subsets of X containing X. In particular, Ex is the largest connected set containing X. Okay, we proved this. Uh, yeah. Okay. Another claim is this. Well, since okay, Ex is closed. Why is that? Proof. Well, Ex is the largest connected set containing X, right? But we know that since Ex is connected, anything between Ex and its closure is also connected, right? Since connected, Ex closure is also connected. But Ex was the largest connected set containing X. Uh, since Ex is the largest connected set containing X, we see that its closure, whatever that thing is, this is connected and containing X, it must lie inside Ex. Hence, Ex should be equal to its closure. So that, and this finishes the proof, right? So Ex is closed. Okay. As a summary, we have the following theorem. If you have any questions, just let me know, okay? Okay, for each x in x, there is exactly one uh, uh, maximal connected subset ex of x containing x. Okay, all right. Uh, Maybe let me write it this way. Sorry. Uh, uh, this ex is by construction unique, right? It is the largest connected set containing x. Uh, for any x in x, the subset ex, which is the largest connected subset of x containing x, uh, is called the connected component of x containing x. Clearly, our metric space is a union of this kind of subsets, okay? And these two subsets, they are largest connected subsets. They have and they are equivalence classes, right? Uh, uh, each ex is an equivalence class, is the equivalence class of x, okay? And we know that if you have two equivalence classes, they are either the same or they are disjoint. So if ex is not equal to ey, then they must be disjoint. So they cannot have a common point, okay? So what we have is then x is written as the disjoint union of its connected components. And each connected component is closed, right? We have seen about that. Each ex is closed. Hence, uh, uh, x is written as the uh, disjoint union of its connected of its closed, they are automatically closed connected components. Okay, all right. Moreover, we have the following proposition. Uh, let X be a metric space and a subset which is both closed and connected, closed and open, which is both open and closed. Then A is connected, and then A is a connected component for some EX. So if you have if you have a subset which is both open and closed, then this A okay, I should say and a connected subset. If A is a connected subset which is both open and closed, then it is one of these connected components. Why is that? Okay, well, since it is connected, okay, proof. Okay, let's note that X can be written like this: A union X minus A. Okay, and this is a disjoint union, and A is closed and open. Therefore, A is open and X minus A open, where both X A and X minus A are open. Now, any AX, any EX is here. So if okay, so I can write this for any X in X. Okay, let me do it this way. Take any X in A, then A is in EX, right? Because EX is the largest connected set containing X, but A is also connected. And we have this. Because this is because X is in A and A is connected. But on the other hand, we have the following. However, we have this. This EX can be written like this. Taking intersection of this with EX, I have this E intersection EX union X minus A intersection EX. Okay. Well, you see that this is an open subset of EX, and this is also an open subset of EX, and they are disjoint. So if both of them are non-empty, then this would give us a separation for EX. However, EX is connected, therefore this shouldn't happen. It means that one of them should be empty, but this is not empty because X is in A and X is in EX, therefore this is not empty. Uh, Therefore this should be empty. Okay, since EX is connected and X is in both E and EX, uh, the other subset X minus A intersection X should be empty, because otherwise EX would be uh, disconnected. Maybe I should write this. EX is a subset of A union X minus A. Okay, right? Because X, this is just X, and I have this. So, and this intersection is not empty. X belongs to this intersection. Therefore, if the intersection of X with EX with X minus A were non-empty, then this would give a separation for EX. Okay, so uh, EX intersection X minus A is empty, but this implies what? EX is in the complement of this set. In other words, it's a subset of A. But A was already a subset of EX, right? And I have this. So thus A is EX. So what we have proved is this. If I take any connected subset of X, which is both open and closed, then it must be one of these connected components. Okay, our metric space is this joint union of these connected components, which are all closed subsets. And here we see that if you have a connected set which is both open and closed, then that subset must be one of these EX. Okay. All right. Well, we have seen that a connected set which is both open and closed must be a connected component, and each connected component is a closed subset. However, the following thing is not true. A connected component, although it is closed, it may not be open. And here is an example. Okay. Consider the metric space Q with the absolute value metric. Okay. Then any subset of Q containing more than one element cannot be connected. Okay, let E be any subset of Q containing at least 2 points. Say R1 and R2, okay, two rational points. Well, between any two rational points, you can always find an irrational uh, number, right? Uh, take, choose an irrational number Q in this interval R1, R2. Well, then I have this. E, of course, is a subset of Q, and Q is a subset of R minus the point Q, because Q is irrational. Therefore, if I subtract Q from R, it is still uh, it still contains Q, but this can be written as follows. This can be written as minus infinity Q union Q plus infinity. And clearly R1 is in this set and R2 is in this set. In other words, the intersection of E with this thing is not empty, and the intersection of E with this thing is not empty. So this means that I can find two open subsets, disjoint open subsets containing E, right? Their union contains E, and each one has some points from E. This means that so E is not connected. Okay. Well, so any subset of Q is not connected if it contains more than one element, right? If it contains two or more elements, then it is not connected. Therefore, any connected subset of Q are just singletons. Okay. Therefore, for any connected subset of Q with the absolute value metric must be a singleton. Must be a singleton. Okay. Therefore, connected components of Q are just singletons. In particular, ER is just R, connected component. R for each R. So we know that Q can be written as the disjoint union of its connected components, right? Connected components. And in this case, these are just singletons, okay? They are just one-point sets. Clearly, each ER is closed because it's a singleton. Clearly, each ER is closed, but it is not open. Why is that? Because, however, ER, which is this thing, singleton is not open, um, because if it were open, then it had to contain an interval, right? But an interval containing rational numbers, of course. But this is a singleton; it cannot contain any interval. Is not open because it doesn't contain any interval of rational numbers. So here we have an example where these connected subsets are not open. Okay, they are closed. We already proved this. Each connected component of a metric space must be closed, but in this example, none of them is open. Okay, none of them is open. All right. I don't expect you to, memorize all these proofs and everything, but you should know what's a connected component, and you should understand basic ideas, and you should be able to follow the proofs when you, read them, but don't memorize these concepts or proofs, but you should know what is, connected set, what is a connected component, and that any space can be written as the disjoint union of its connected components, and these connected components are closed subsets, and so on. Okay. What else? Yeah. Okay. Okay. Well, I have actually one more result, but let me do it next time. So next time I'll do two things. So I'll prove this proposition. Remember, I mentioned this counterexample. Where was it? Topology sine curve. Yeah, I said this set is connected but not path connected, right? In other words, you cannot connect any two given points on this set. Indeed, if you choose a point like this, okay, one point on this component, this is clearly connected because it is the image of the real line. It's a copy of the real line. And this red curve is also connected because it is also the image of a continuous map. It is just the graph of sine 1 over x. Both of them are connected. So this is one connected component. The red one is another component, path connected component. Actually, this whole space is connected. We will prove that. But we will also show that you cannot find a continuous path joining this black dot to this black dot. Okay, there is no continuous path joining these 2 points, and the reason is actually clear. You see, this curve gets closer and closer to the y-axis, but it never touches that line, and it goes up and down 1 unit up and then 1 unit down. Therefore, you don't get a continuous path. I mean, if you wanna start from this point, you will travel an infinite amount of path distance, but you will never reach this point. Uh, and a path should have a finite kind of distance, I mean length, right? But here you have to go up and down infinitely many times, therefore its length will be infinite. We will prove this next time. And then of course there comes the question that okay, R2 has some subsets which are connected but not path connected. How can we guarantee a connected subset is path connected, right? And here is the result, which I will prove next time. Okay, yeah, I'll prove namely this: an open connected subset of Rn is arcwise or pathwise connected. So I'll prove this theorem, and this will be an answer to what I asked a minute ago, right? There are some connected subsets, but they are not path connected. So how can we make sure that a connected set is path connected? Well, if that subset is also open, then it is automatically arcwise connected. Okay, so open connected subsets of Rn are arcwise connected. Clearly, the topology sine curve is not an open subset of R2. Okay, so next time I'll prove this theorem and talk about that example, and actually I'll talk about one more example, and we will finish our discussion on connected metric spaces, and then we will pass to what applications. Do you have any questions?